All right. So in this video, we'll talk about the acid strength. Okay. So the strength of the acid is all about its K value or Ka value. Okay. So if we have an acid, we know that when it reacts with water, it's going to establish this equilibrium. Okay. And H3O plus and A minus, which is the conjugate base AQ. Okay. Now, if we have greater the amount of products we have compared to the amounts of reactants, okay, stronger the acid is. That's the idea. Okay. So again, we know that Ka is equal to H3O plus concentration times A minus concentration over HA concentration. Okay. The idea is if we have a larger Ka value, stronger the acid is. Okay. So higher the Ka, stronger the acid. Okay, that's the idea. Now, how can we change this this Ka value? Okay, for an example, let's say that we want to make an acid stronger. Okay, what can we do? The idea is the reaction always occurs from less stable to more stable. Okay, and then if we can somehow increase the stability of our products, then we can increase the Ka value. Okay, to increase the stability, we need to play with the structure. Okay, now the thing is, when it comes to our products in this equilibrium, we have H3O plus and A minus. H3O plus structure we cannot change, but the conjugate base structure, which is this substance over here, can be changed. Okay, based on the substance we use. So we will be focusing on the factors that stabilize the conjugate base. Okay, and then thereby we can predict whether a given acid is stronger or weaker compared to another acid. So that's the idea. So again, we'll be focusing on the stability of the conjugate base. Okay, so this is stability. Okay, more stable the conjugate base is, more product favored this reaction is going to be, and then thereby we're going to have a greater Ka value. Okay, now let me write this down here as well. So more stable the conjugate base, stronger the acid is. Okay, so that's going to be the entire idea about determining the relative strengths of acids. Okay, the acid that generates the most stable conjugate base will be the strongest. Okay, now with that, let's see if I can have okay another page. Okay, now let's think about the features that we can consider to determine the stability of the conjugate base, stability of the anion. Okay, so there are three features we consider. Say the features that determines the conjugate base stability. Okay, there are three features. One, the nature of the charge bearing atom. Nature of the charge bearing atom, because we know that In our previous example, when the weak acid reacted with water, it generated the conjugate base, which has a negative charge. And now, what in the first feature, what we are focusing on is this atom that carries the charge, that bears the charge. Okay. Now, what we have seen is if you're comparing two acids or acids in that generates conjugate bases, where we have the charge bearing atom in the same period. Okay, let's say the same period. If they're in the same period, okay, higher the electronegativity of the atom, more stable the conjugate base is. Okay, higher the stability of the conjugate base. If we are comparing acids that generates conjugate bases, where we have the charge bearing atom in the same group, then it's not the electronegativity, it's the size that determines the stability. Okay, in this case, greater the size of the charge bearing atom, higher the stability. Okay, and we'll talk about this a little bit more in detail in a bit. For now, let's consider the second feature. The second feature that determines the stability of the conjugate base is the charge delocalization. Charge delocalization. Okay, so in other words, resonance. Okay, anions that have resonance stabilization are more stable than the anions that do not have resonance stabilization. This is true for any ion, by the way. Okay, ions with resonance stabilization are more stable than the ions without resonance stabilization. Okay, the requirement is there should be a double bond, one bond away from the charge. Okay, requirement is there should be a double bond, one bond away from the charge, or from the charge bearing atom. Okay, that's the requirement for charge delocalization. Right, and the third and the final feature is called the inductive effect, or it's about the neighbors. Okay, the inductive effect. The idea here is the electron withdrawing groups. Okay, let me call this electron withdrawing groups. E stands for electron, W stands for withdrawing, and G stands for groups. Okay, stabilize anions. Okay, and electron donating groups, on the other hand, destabilize anions. Okay, or stabilize the conjugate base. That's the idea. Okay, now what we're going to do is we will consider these three features one by one. Okay, so let's start with feature one. Okay, so the feature one is the nature of the charge, nature of the charge bearing atom. Okay, to illustrate this, Okay, so feature 1B, 1A, it's about if in the same group, right? Same period. If in the same period, then having the charge on high electronegativity atom, it's going to be more stable. That's what we discussed before. Okay, now let's illustrate this. Let's think about two acids. Okay, I mean two substances. Let's think about CH4. Okay, if this is going to act as an acid, it's going to generate CH3 minus. This negative charge will be on the carbon atom, and then HF. Okay, if this is going to act as an acid, which it does, it's going to generate F minus conjugate base, and the charge will be obviously on the fluorine atom. Okay, the idea is if you compare the carbon and fluorine, okay, let me have a different color. Electronegativity wise, fluorine is more electronegative than carbon. Okay, therefore F minus is more stable than CH3 minus. Okay, because in CH3 minus, the negative charge will be on the carbon atom. In F minus, the negative charge will be on the fluorine atom. Since fluorine is more electronegative, it's going to be more stable. Okay, because electronegativity is all about the attraction towards the electrons. If we have strong attractive interactions with the electrons, you're going to have a lower potential energy. The stronger the attractive interactions, lower the potential energy, and that's why fluoride ion is more stable than CH3 minus ion. Okay, and as a result of this, okay, you can expect HF to be a stronger acid compared to CH4, because, okay, let me write that down. Therefore, let's say the Ka value, okay, Ka of HF will be greater compared to the Ka of the CH4, which is true. Okay. In other words, HF is stronger as an acid. Okay. Therefore, HF, let me write it in a different way. Now for acid strength will be greater in HF compared to CH4. HF is a stronger acid compared to CH4. Okay, and that is how we use that's how we use the first feature if our charge bearing atom is in the same period. Okay, and now the other part of feature 1 is, let's say 1B. Okay, if the charge bearing atoms are in the same group, okay, if they are in the same group, then the size is more important. Greater the size, higher the stability of the charge bearing atom or the conjugate base. Okay, example. Okay, let's think about simply HF and HCl. Okay, let's think about HF and HCl. HF and HCl. HF will generate F minus as the conjugate base, and HCl will generate Cl minus as the conjugate base. Okay, they're in the same group, but Cl minus is larger than the fluoride minus ion. Okay, the size, let me actually have to have a different color. Okay, size of Cl minus will be greater than F minus. Okay, therefore Cl minus is more stable than F minus. Okay, if that is the case, since we have the more stable conjugate base in HCl, HCl will be stronger. Or we can do the same here, same thing we did before. Therefore, the Ka of HCl will be greater than the Ka of HF, meaning HCl is stronger, strength wise. Okay, HCl will be a stronger acid compared to HF. Okay, and that's how we use feature 1 to determine the relative strengths of acids. Okay, and keep in mind feature 1 is more important than feature 2, and feature 2 is more important than feature 3. Okay, now let's move on to feature 2. Feature 2 is about charge delocalization. Okay, charge delocalization, okay, or resonance. Okay, now to illustrate this feature, let's take an example. Okay, let's take CH3 CH2OH and CH3 COOH. Okay, if I draw these structures, this is CH3 CH2OH line structure, and then this is CH3 COOH line structure. Okay, and from CH3 CH2OH or ethanol, you're gonna get, if this is going to act as an acid, then it's going to generate this conjugate base, because once it's loose, once this proton is donated to water, it's going to generate this O minus ion. And then in the case of CH3COOH, okay, we still have that negative charge on an oxygen atom. Okay, because between carbon and oxygen is more electronegative. Therefore, the oxygen protons bound to oxygen will be more acidic. That's why we remove the protons from oxygen OH in both cases, not from carbon hydrogen, or not without breaking a carbon hydrogen bond. Anyways, now the thing about we have a different color. The thing about this anion is, if I redraw the structure, okay, what we actually have is we have a lone pair, and then we have the negative charge on this atom over here, right? And then what could happen is, because we have this charge minus charge one bond away, okay, here's my one bond, let me color, okay, one bond away from a double bond, here's my double bond, okay, here's my single bond, which is one bond away. Okay, so my charge is one bond away from the double bond, and as a result of that, this charge can get delocalized. So you can move the electrons like this and then transfer the charge to the other oxygen atom. Okay, so when this happens, you can is the negative charge here. Okay, so this charge can be transferred like that. Okay, so now what we're noticing here is, okay, then again, even here, we can have the same thing. Okay, it can also go back to the previous structure, and then it will generate what we have on the left-hand side. Okay, so at the end of the day, what we're going to see is this negative charge in this species is delocalized between 3 atoms, right? So if I redraw this structure one more time, okay, here's one oxygen, here's the other oxygen. Now this negative charge is spread between 3 atoms, 2 oxygens and it's 1 carbon here. Okay, when we have a situation like this, when we have this charge delocalized over a large space, or electrons delocalized over a large space, then both potential energy and kinetic energy goes down, and as a result of that, it's going to be more stable. Okay, like that, it's going to be more stable as both potential energy is sub P and is kinetic energy are lower when we have charge delocalization. Okay, and the point is, when we have two conjugate bases or 2 anions, okay, if one has the resonance stabilization, this is also called the resonance or charge delocalization, that ion will be more stable than the ion without charge delocalization or resonance. Okay, and that's why we call this resonance stabilization. Okay, resonance stabilization. Okay. Now there is feature 2. There's an entropic aspect as well, which I'm going to talk about in a different video. But if we have 2 anions, one with charge delocalization and one without charge delocalization, the one with charge delocalization is more stable. So that's going to be the point of feature 2. Finally, if we move to our last feature, feature 3. Okay, feature 3 is about the inductive effect or the neighbors. I'll let you know what I mean in a second. The inductive effect. Okay, to illustrate feature 3, again, I'm going to use an example. Okay, let's say that we have two conjugate bases. Okay, so let me drop that for a second. Okay, so let's say that we have this situation over here. Okay, so we have this conjugate base, the CH3 group. Okay, and then we have another conjugate base, but this guy had the same CO minus part. Okay, and then but here instead of CS3 we have CF3, fluorine, fluorine, fluorine. Okay, now in this case you can see that we have the same anion in both cases. Okay, same anion in both cases. This is my anion, this is my anion, but the neighbor is different. Okay, so in one case, when we have CF3, we know fluorine is the most electronegative atom we know, and that is going to pull the electrons away from this negatively charged center. Okay, because of the electronegativity of fluorine. Okay, is going to reduce the electron density in this anion center, and as a result of that, the reducing the electron density in an anion center stabilize the anion. Okay, let me write that down. Electron withdrawing groups reduces or decreases the electron density of the anion. Okay, electron density is reduced of the anion, and as a result of that, therefore the stability increases. On the other hand, when we have groups like CH3, okay, they are actually not electron withdrawing; they are considered electron donating. Okay, they are not pulling the electrons away. Instead, they are trying to donate the electrons. Okay, so electron donating neighbors, or electron donating groups like this, electron donating groups increases the electron density of the anion center. Okay, therefore the stability of the conjugate base, or the stability of the anion, decreases. Therefore the stability decreases. Okay, and since we have the most stable anion of the conjugate base when we have electron withdrawing groups, okay, and those acids will be stronger. The acid that produced this conjugate base will be stronger than the acid that generated the conjugate base that does not have those electron withdrawing groups to stabilize it. Okay, and just to I'll give you some examples of electron withdrawing groups. Okay, anything that has a high electronegativity, okay, can pull the electrons away from the anion center. Okay, so examples which I've seen here, like a CF3 group, or any fluorine atoms bound to it, or carbonyl groups. Okay, they tend to, even the phenyl groups actually, okay, they tend to pull the electrons away from the anion center, and then thereby they're going to stabilize the anion. And on the other hand, electron donating groups like, say, CH3, CH2CH3, or anything that has only carbon and hydrogen are considered electron donating, and they actually pushes the electron density towards the anion center, making it destabilized. All right, so we have summarized all the three features that determines the stability of the conjugate base in this video. I hope you find this video helpful. I'll see you guys later in class. Bye, everybody.